Hello and welcome back. Last time we stopped with this program that could multiply two numbers. Let's just give that another try so we can see it working. It has been a week. Let's see, 11, let's use big number. Actually, let's not use a big number, let's use a smaller number. Let's use 3. Times 42. Always a good number. 42. We're gonna let this run for a bit. That was the output 126, which should be right. Yeah, that's right. And this is our program. So got the code. Once again, we read the two numbers. We skip ahead if there's no multiplication necessary, and then we would just repeatedly add b to a. Oh no, sorry, we repeatedly add b to the sum and subtract 1 from a, then repeat until a is 0, and finally output the result. Works perfectly fine. It represents our simple arrangement with repeated addition. If the view would show up, hello, there it is. So our concept from last time. This solution works, but it has some downsides. One major downside, especially. To show that, let's go back to just the CPU view and include this little thing in the bottom right, the instruction count, because that's our biggest issue. That's why I didn't use a big number. This method works perfectly fine, but its runtime can get quite long depending on our value for a. Let's load the program again. Let's just make a few experiments. So let's start with a0, b0. Oop, that is a0, b0. We have, well, let's just put in the notes maybe. Let's write that down. A0, B0 gets us 4 instructions until we have the output. Let's just leave the instruction table on the left. Actually, no, let's move on to the new sheet. So A equals 0, B equals 0. 4 instructions. Now, of course, we know that the value of b doesn't really influence the runtime, so actually let's try that again just with a proper value for b. So we leave a at 0, let's b, let's just use 1. Just make it as simple as possible. Next simplest version next to just 0. So a 0, b1, still 4 instructions. Let's try the program again, this time with 1 times 1. Move forward, that is after 12 instructions, so a equals 1, b equals 1. I don't think I have to repeat this all the time, right? We get to 12 instructions. Let's just make this in a table. So with b equals 1, so we get for an a so for 0 we had 4, for 1 we had 12. Let's repeat this a few times. For next one we use 2, use this till 1. Clicking my best. Output is 2 at 20 instructions. Let's use maybe 2 more. Let's try once more with a equals 3. Instruction 1. Move forward a bit. Oh. Into bit 28. 3, 58. We can see the pattern already emerging, but just to be sure. I mean, it's pretty obvious why this pattern appears. I don't think I have to actually explain that. Let's just get for as well. 36. Oh, we're at 36. So, if we look at the runtime, depending on A, we get an increasingly higher runtime. It takes longer and longer to calculate the result, which makes sense. We're just adding, and adding takes a fixed amount of time, and for each value we go higher in A, we add this fixed amount of time to the runtime. So if we look at it in a graph, like if this is A, sorry, I'm jumping ahead. This is A, this is runtime. At 0, we start already up here, the fixed amount, and then we just go up in a linear line. Just the higher A is, the bigger the instruction count that we need. So we should maybe make this a bit more dramatic. Since this does take quite a bit of instructions, it should actually be a lot steeper. Not bad. I don't like this. I don't like this. I can write on this properly, I swear. Let's make proper lines here. Nope. Let's make a straight line there. Let's make a straight line here. Instructions A, and then start further up, and then we go on a straight line. So that's a bit of an issue if we want to calculate pretty high numbers. So if I were to input in 100 for A, well, this is probably gonna take a couple hundred instructions, right? So the pattern seems to be we start with a baseline of 4 and we can add 8 instructions for every value of A. Yeah. We want something faster. How can we get faster? So we're getting kind of distracted. Something is happening outside. I think I can ignore it for now. Well, to get it faster, we have to find a better algorithm. So far, our approach was multiplication can't be done directly, so let's use just addition, which can be done directly. And according to our instruction set, we have an add command, and we just repeat that a few times, and that's how we get our multiplication. Well, there's a trick we can use. We don't have multiplication in there still, but we have something else that sort of multiplies. Let's make this little excursus into numbering systems. Let's say the number 1, 2, 3, 9, 7, 8, 1, 2, 3, 9, 7, 7, 5, 4, 4, 4, 4, 4, 4, 1, 0, 0, 0, 2. Why is this? Never mind. Again, doesn't matter. This is a pretty big number, I'd say. If I were to give you the task to multiply this by, let's say 3, it would probably take you a bit, unless you had a calculator. Even typing this in would take a bit. But if I were to tell you to multiply this by 3, no idea. If I were to tell you to multiply this by 10, you would immediately know the answer. You would immediately know. I just put a 0 in the end. That's it. Like, this is it. Multiplying by 10 is simply add a 0 in the end. In the same way, you could also argue that dividing by 10 is equally easy. I mean, you can't really add a 0 in front. I mean, you can do that, of course. It's still a valid number. But you just move the decimal sign. Like, we know that technically every number has a decimal and then 0.0. At least every natural number has this. So if we multiply by 10, we move the decimal point to the right, or move it to the left if we divide by 10. So we don't really need to worry about what numbers are in front. Like, that doesn't matter at all. It could be any combination of numbers, could be any number at all, no matter how many... Okay, seriously, what's happening? Okay, I'm gonna ignore that. It's gonna be hard to ignore because it's kind of distracting. Any number in front, we could easily multiply or divide by 10. Multiplication is even easier because we just have to write a 0. Not worry about any decimals. Well, this works because our numbering system is decimal system. So we work with base 10. We have 10 different numerals. Is it numerals? 10 different symbols. Let's use that. 10 different symbols we can use at each position. And once we used up 10 different positions or 10 different symbols, we just go back to the first one in order and just increase the one on the left by 1. And once that one has gone through 10 changes, we increase the one on the left of that, and so on. And other numbering systems exist too, which have the same principle, they're just not based on 10. Like binary, the system we use for computers, which just has 2 symbols, 1 and 0. So if I have this string, I'm too lazy. If I have this string of 1s and 0s, and I'm going to calculate this. It's also straightforward. I just have to add a 0 here. The thing is, I didn't calculate times 10. This is a binary number. This is not the decimal 10. This is the binary 2. And every numbering system is the same. If you write a 1 and a 0, in decimal that's a 10, in binary that's a 2. In ternary that's a 3. In hexadecimal that's a 16. So 1, 0 is in every numbering system just the value of the base of that numbering system. So in binary for us, that's a 2. So adding a 0 in the end is the same as multiplying by 2, just as adding a 0 here is the same as multiplying by 10. And just moving over all these numbers to the left and adding a 0 is a very, very simple task. It's not really multiplication, it's just shifting a few bits to the left. And the same way, we can also just shift them to the right. Can also add a 0 in front, which doesn't really change the number. But yeah, just shifting over the number to the right. Remove digits from here in the end. It's basically dividing by 2. Just as how moving or removing decimals, removing numbers from the right at top here is dividing by 10. And again, bit shifting to the left or to the right isn't really an operation. It's very simple. It's just a few commands that shift over a couple of bits internally. No calculation needed. That's why multiplying by 2 and dividing by 2 is a built-in function that we do have. That's the bit shift. Bit shift left, bit shift right. So these commands are basically just multiply by 2, divide by 2. So we do have some form of multiplication. And since we have a minimal amount of multiplication, we can do something interesting. I'm just gonna remove this. Let's make some space again. You probably have learned this way of multiplication in school, or have seen it somewhere else. At least that's how we learn multiplication. Big multiplication, like what's that? Written multiplication? Long form multiplication? Like 137 times 17. Where did I pick those numbers? I think I'm attracted to prime numbers today. Is 137 even a prime number? Look, I'm not going to think about it. Anyway, if I want to multiply these numbers, so what I would do, I would multiply 7 by 7. That's 94, 7, wait, is it 94? 49? Yeah, it is 49. Oh, I didn't get that wrong. 7 times 7, then 7 times 3 is 21, but I I'm moving one digit on the left here to now add a 0 here, and then just 2, and 7 times 1 is just 7, but this time I have to add 2 zeros. 7. And now I can do the same with the 1 in front here, which I'm moving one digit to left, so I have to add a 0 already. That's a 7. Then one digit from the 1, another one for the 3. That gives me a 3. And then lastly 1 and 1. 1 plus 2 is in here, and that's a 1. And now I have a couple of different numbers that I just have to add up. So that's a 9, that's a 12, carry 1, 4, 13. So 137 times 17 is 2329. Long multiplication, whatever the name. And we can do the exact same thing in binary, of course. This works in any base system. So 101 times 11. Let's just use the same number of digits, make it smaller. So 1 times 1 is 1, times 0 is 0, but let's keep that in here anyway. We have to keep in mind always adding zeros because we're a couple of digits to the side. So 1 times 1 is 0, 0, 1. And the same with this digit. We have 1, 0 anyway, and then 1, then 0 and 1, and then we add them together. We have 1, 1, 1, 1. Thing is, in our base system, 10, it's a bit complicated. You have to make all these different steps one by one because each of these combinations, all 6 variations, can have different... How do I put this? It's not easy to predict which number would be coming out of the individual results. Is that a good way to phrase it? Look, you'll see in a moment what I mean. With binary, we only have 2 options. We either include the number or we don't. We don't really have to multiply. Here I have to multiply 7 times 7, 49. And here I just have to think, is there 1? Is there also 1? Then it's a 1. Is there 1 but there's a 2? Well, that's a 0. Is there 1 and there's not? Is there 0? Then it's 0. It's always, it's a 1, 1, then it's a 1. If it's at least 1, 0, it's 0. So in other words, this is the same as 1, 0, 1, to include for this one, and 1, 0, 1, 0. We just added 0 in the end for this one. So unlike with our decimal system, we could just use one of the values here, shift it over depending on the position, and simply choose to add them or not add them in our list here for our adding, depending on the one in there. I made it sound super complicated, didn't I? Let's use a bigger number to demonstrate again. It is a really, really simple system. It's super easy. In fact, it's so easy that you can create electronic circuits that can do multiplication. That's actually what happens in computers a lot. Like, it's because it's so simple and doesn't really require any advanced computation, you just have some hardware that can do it on its own. You have these matrices that do look similar, at least the schematics look similar to like the long-term multiplication, long-form written. Doesn't matter. So let's use a number. What's width today? Use a bigger one. So I'm gonna make my life easier. I'm not a computer, so I'm just gonna take the cheap way and I'm just gonna assume I'm repeating this for every digit in here, just 4 times. But then I have a first digit as a 1, so we include the 1, 1. Oh, we have a 0 here, so that's My bad. So that's a 0, 1, 1, 0, 1. Just include the full number on the left once. Then we shift over to the left by 1. We have a 0 in here. Well, that means we can skip it. We don't need to do anything. Then we just shift over another digit. We just add another 0. Here's a 1, so we have to include the number. That means 1, 0, 1, 1, 0, 1. And here we shift over last time. Like that. It means we had 3 1s in our number here. That means we only have to make 3 different values, which are just directly this original value shifted over. So every time we had to add a number, we didn't have to do any multiplications. We just took the original number and shifted it. And then we can add them all together. So 1, 1. This one is 1 with a carry. This is 0 with a carry. This is 0 with a carry. This is 0 with a carry. It's 1. Like that. And no, I'm not going to translate that number. You can do that as homework if you want. Now, this is long multiplication in binary, which can be simple, so to speak. And we can repeat this in code because we know how to shift. We have the command for that. We have the bit shifts, which can just add a 0 in the end and shift our whole number over. So creating these numbers is super easy. We have the original number, we just take it and shift it over depending on which digit in here we're looking at. And for each of these digits, we just have to decide, do we add the number or do we not add the number? Another way to look at it would be if I put it up here. So we still have the first one in here, third one in here, fourth one down here. And for the second one, well, we can still shift the number over. Let's use a different color actually. No, not that one, that one. And we shift over by 1 and then 0, 1, 1, 0, 1. That's it. Just we ignore this one. Here's a 0, so add this, calculate. Just simply ignore this one result, but every single step we get down here, we just took the original number and shifted over by 1 to the left, shifted over by 1, shifted over by 1. And every time we just decide, hey, do we add this number based on one of the digits in here? So this is the next question. How do we get the individual digits in here? Well, we can use bit shift again. Just this time we shift to the right. This has to do with the ALU flag. I mentioned before how in case of over or underflow, our little flag is set, and we have a jump instruction that can react to that flag. Well, that goes for bit shift operations as well, in a slightly different way. Basically, in our computer, just a reminder, we have exactly 8 bits, so 0, 0, 0, 4, 5, 6, 7, let's use a 1 in here. And that's exactly 8-bit, and that's fixed. We always have 8-bit. Exactly. So if we shift this whole thing to the right, well, the 1 fell out of our little memory range, and we just fill in the gap on the left with a 0. This is our new number after the bit shift to the right. If this is a 1, we set our flag. If it was a 0, we don't set the flag. Basically, we set the flag to whatever number was just moved out through the bit shift. Same happens in the other direction. If there's a 0, do nothing. If there's a 1, we shift to the left. And this one is setting the flag. So by shifting to the right, we can get this first digit. Just shift the entire number to the right and then check the flag, and that's how we know if this bit was set. And then we can, well, that's 1101. We shift to the right, then flag is set. Shift another time, then it's going to be this digit, and the set is unset. Should probably not put this. Not set. Then shift it again, and then this digit is moved out. It's set again. Then this digit, the fourth, it's set again. And every time it's set, we have to add the number. If it's not set, we can skip it. We still shift the number over technically, or input, but we don't add it to the sum in the end. Set, not set, 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 and get the result. Another thing, as I mentioned, as we shift to one direction, we fill the hole on the other side with a 0. So if we shift to the right, we add a 0 on the left. That means after 8 shifts, our number will be just 0. And there's noise outside again. Okay, truck's gone. That means, whoop, that wasn't undo. At most, we would have to repeat this 8 times, because we only have 8 digits. The actual value doesn't matter, it's just how many digits are present, 8. So at most, we would have to repeat this 8 times. After 8 shifts, there's only 0, and there will never be another bit we can set. And that means that at most, no matter what number will be input, after 8 shifts we will have our result. There's an upper limit of how long the operation can take. Technically, this old method, this straight up add, has an upper limit as well. It's simply the highest number we can input has 255 additions. Well, let's say 254 additions if we start with the number itself. This one has at most 8 additions. So you see the difference, 254 to 8? That's a bit different. Plus, in this case, it's not even fixed. Just so for a smaller number we stop early, this one can also stop early. Since after 4 shifts, the entire number is already 0, we can simply check for that. We can simply test if our number has reached 0, if there are any ones left in there, and if not, we can just go to the end. We don't have to make the additional shifts anymore. So in our example here, after 4 shifts to the right, we know we are done. We have our result. So not only is it fixed at most 8 repeats, it can also abort earlier, way earlier than this one, based on the amount of digits that are set. And because this is a base system, we're talking about every digit is twice the value of the previous one. And if you're not quite following what I'm getting at, basically to require an additional shift, to require one repeat of the whole process and one additional addition, we have to double the value. Until we double the value, we will just stay at the 4. Okay, double the value is not quite true. In this case, just adding 3 would be enough to get a 1 in front here. Okay, let's be fair. But once we reach the first digit here, we have 5 shifts, and then we need to double that value again before we get to the 6th shift. So if we look at the graph then, same graph as the one above, or the one left. So input, yeah, okay, let's use the same A as input. Instructions Okay, instructions are a bit more complicated than that, but the basic idea is to get, let's say we also start here as a higher value. It might take this amount for the first shift, and it would take the same amount for the next shift, but we need to double the value first. So this is actually the next value. Then we go one more up, and then we need to double it again. So instead of a linear curve, or linear graph, we get this curve. Okay, that last part doesn't look good, but this means this algorithm will be way more efficient when we go to the higher numbers. This whole thing here, this is a concept you will find later that you will have to tackle with, called the complexity. Specifically what we're looking at right now, we could see this as the big O notation for these two different instructions. This would be an O of n, because it's linear, and this would be an O of log n. Yeah, whatever. Linear growth, logarithmic growth. One is gonna cost us a lot of instructions pretty quickly, and the other will be actually slowing down over time. As in terms of growth. It's weird to say it slows down. The process doesn't slow down, it's just that high numbers will probably result in a better runtime than this. So we're gonna repeat the same values for our new algorithm later. We have to first get to that though. Now let's go back to here. Let's quickly erase the old one. No, that's fine. We have to design the new algorithm. So let's quickly look at the conditions. We have one value that's constantly shifted to the left and might be added to some or not. And then we have another value that's constantly shifted to the right, so we can determine if the first value needs to be added or not. And because we also need these two numbers to be input at some point and stored in the memory, let's just do the same as we did before. We're just gonna use the existing memory addresses where we put in the numbers in the first place and change those. So we're gonna need to read the numbers first. Read A and read B, our two input numbers. And then we need to check if we need to add A. For the first digit, we don't increase it yet. We just take the original A, and depending on B, we might shift it over or not. So to check that, we have to now shift to the shift A or shift B. Actually, which one do we go? The last one, it's A that was reduced. Let's keep that maybe. In the previous one, we constantly reduced A. That makes more sense also for the table here. And B was the one that was constantly added. So we're going to shift over A to the right. To the right. You probably can't read this, can you? Shift A. Right, like that. Then check if set. If it is set, we have to let's do it this way. Yes. Then add B to more spacing in between. Add B to not sum, product. More fitting this time, since we're not doing continuous additions anymore. It's not as simple as a sum. If not, well, we're gonna actually do the same as we do here. After we've added B to the product, so we decided the first bit was set, so we're gonna add the first value to our product. We've included the first one in our sum for these in between products, in between values. But then we have to also consider the shift to the left. So we're gonna have to shift. Let's move it apart. Let's also use shift B left, like that. So we increase the value by 1, so we can account for the next digit, the next iteration. To the left, and that's also what we do if we did not have to add it. So if it's no, we just go directly to shifting B. So now we have a new value we can use for the next time, and we've reduced A by, well, we halved it. We divided it by 2 basically. We reduced it by 1 bit. Now we have to decide if we repeat the whole process. And actually that's something we have to do on top here. Because if A is 0 at this point, well, we can just directly end it, right? So check if A is 0. Check if A is 0. And if no, we can just go repeat the continue with the process or repeat the process or whatever. And if not, if it is 0, we can just output product. However, if down here we shifted B over and we've added it to the product if necessary, then we have to go back to the start, always. That's gonna be our program. Let's open the code. Let's rewrite this part. Not this one, this one. Alright, so this was our old program. Let's reuse some stuff. We're gonna need some values down here to store and to output it, and we need to read that stuff. But this part in between has to go. Right, so we read A and B. Check. We output the values or the product. Check. And we have some memory addresses to store the values. Check. So what was our first task on the list? We check if A is 0. And if A is 0, we go directly to the output. Well, actually, we can do another step. One that we did last time as well, that I'm not reading down or writing down here right now. We can first check if B is 0 as well. 0. No, that means we have to Yeah, no. Jump of 0. We can use the fact that right now B is written into the accumulator anyway. No, it is not. Ah, forgot. We write it into the memory address. So we have to first write B into the accumulator. Then we check if B is 0, and if it is, we go directly to the end. And product is going to be 0. Then we have to check. So we're covered this. Check, check, check. Then we have to cover this part. Check if A is 0. So see A, jump of 0, and if it is 0, we jump to the end. Check. If it is not, we have to shift A to the right. Well, A is already in the accumulator, so we can just bit shift to the right. And to not repeat the mistake from last time, you've learned your lesson, you specifically, not me. Shift to the right, and then we store that value back into A. So we have it for next time. Done. And then we have to check if the bit is set, the ALU flag, whatever, is set. Jump a flag, and we're gonna jump to Shift B, I guess. We haven't decided the name yet. Right, there's a mistake. This is a little issue we have to contend with now. Jump a flag means it will jump to that part when the flag is set. With our logic, we want to jump ahead when the flag is not set. So we have to invert the condition somehow. So what we can do, let's see, we need some address here later. We make a jump instruction that actually goes where we want. If the flag is not set, we are going to run to this command down here, and then we can jump to Shift B. And then the instruction that comes after this, that wouldn't be reached, can be the one we actually jump to with this jump a flag. And this is going to be the add B to product. So add B to product means we have to first write product to the AC. Then we have to add B. Then we have to store it back into product. That's right. And this is the add B. This is where we jump to add B. And down here then we write B to the AC. We bit shift to the left and read AC B. And this is gonna be the shift B. So let's move this about a bit. Like this. So what we have now is we shift A to the right and store that result. If the flag is set, if the bit we just shifted out of A was set, we go down here, which we'll call this code that simply adds the current value of B to product and shifts over B to the left by 1. However, if the flag was not set, if that was 0 we shifted out, well then we're gonna hit this jump instruction and go directly to the shift over B. So this is how we can invert the jump, invert the condition. We add another jump and just basically pretend like the address we jump to is directly after our jump, and you see the result. Let's not talk about it. Just gonna get caught up in details again. But anyway, this makes completion of this and this and this. Only thing left is this jump back up. Let's jump back up. Where do we need to jump back to? We need to check if A is 0. So we go back up here. Let's repeat. Jump to repeat. And actually, that's it. If I didn't make a mistake, this should already be our finished program. Let's try that. I made a mistake. Doesn't compile, so let's go back into the code and let's see where I made a mistake. So we have A and B exist and exists at B, shift B, shift B. Oh, there. Put the symbol. Yep, now it's loading. Alright, let's try that again. Just first, let's input a number. Let's use a different one for instruction 3. So 7 times 3 should be 21. Well, let's go back. It is indeed 21. So calculation seems to be right. Now let's try the whole thing again with our little table. So let's put notes, and yeah, you can't see it this way. Let's move it over to the side. You can see it either. Let's just make it smaller. Let's put it in between here. Actually, you don't need to see it, do you? Just return this in the middle. Like that. And just show you the CPU view. You don't really need to see the table. Oops, that was the cable for the power. That's not good. Let's plug it in quickly. This didn't break anything, did it? Did I break anything? Did I break it? Hope I didn't break it. Check, do the nodes still work? Oh, nodes. Okay, the nodes still work. Back to the CPU. Ooh. Should be careful. The USB plug is not snugly fit in there as it used to. Okay. We're gonna start with 0 times 1. We're doing the same input as last time. And there we are after 6 instructions. Let's write in the same table 6. Now let's try again. We enter 1 and another 1. And the output is 1 after 18 instructions. Let's try again. And I input a 2 for instructions. We input a 1 for instruction. And result after 28. Number's getting big. Let's try again. Instruction 3 points. Oop. And 1 for instruction. $30. Load the program again. Let's try 4. Let's try the 1 again. $38. So if we look at the values now, you can see that for the most part, the numbers look worse. So despite our algorithm technically being better, at least if we look at the complexity at the big O notation, this is a smaller value than this. Like, it should be faster on your algorithm. But so if we compare the values, we go from 4 instruction to 6, 12 to 18, 20 to 28, 28 to 30, okay, that's not too bad. And then we jump ahead to 38 again, instead of 36. So, what's going on? Well, that's the issue with the big O. It doesn't really tell you the full story for your use case. It's just a rough idea of things, how they work out. Especially for small values, they don't really give you accurate numbers. The thing about big O notation and these estimates is that they tend to approximate the results when you get to really high numbers. Because you skip out a lot of stuff. Like, they are reduced to the most essential graph, so to speak. But there are always constants involved that automatically are skipped, or certain terms are just completely removed, even if they influence the runtime. Just so super simplified, which can help if you compare algorithms. Because in this case, for example, I still am gonna use the second algorithm we input, the one that we just programmed. Let's test y with some bigger numbers. So let's start the program again. This is still our advanced program. Let's input, let's say 20 times 20 times 12. Going forward. So for a value of 20, actually I should make the entire result, sorry, I should make it an accurate comparison. Should put in 20 into 1. The result was indeed correct. Well, let's try it again with just the 1. So this is for the advanced version, which now takes 60 instructions. Let's input the old one again. I'm just gonna copy out our current program, save that over here. Then we're gonna input our old one and load again. Let's see what this does. I'm gonna input 20. I'm gonna input 1. And let's wait until it's finished. So 60 is what the old program, or the new algorithm does. We passed 60. Yeah. This is taking a bit. There we come to, yep, there it is. So, we're at 164. So, this is the nasty part of Big O. If we look at our results, just our measurements here, very thorough, 5 different measurements, well, sort of thorough. And it shows us that the first algorithm is kind of better. It's not landslide, but it tends to be better. If we look at 2 especially, yeah, no chance. But then we look at the higher numbers, and suddenly our new algorithm doesn't so bad anymore, right? I mean, 2.5 times, that's not bad. Close to 3 times. And this is the stuff you use the big O notation for, just to give you an idea, how will it perform in the long run? This was mostly an exercise just to get some more practice with the assembly and to get you thinking into algorithms. I didn't intend to really discuss Big O today, but I think it's a pretty good example to show that pretty directly. Instruction count is super useful for this right now. So yeah, we got some practice in. You saw a different algorithm. We discussed some more possibilities of this made-up CPU. Let's move on to something more interesting. Last time, we made the switch from machine code to assembly. And I think because we made the switch to assembly, we now had a relatively easy time with creating this program. I would not want to write this in machine code directly. That's, no thanks. But still, this is kind of obscure. Like, if you had no idea what coding does, and you look at this, like, if you didn't have any previous knowledge about programming or assembly, you have no idea what's going on, would you be able to figure out what this does? I mean, I'd argue even someone that does know programming would have a hard time really getting into this, because these are very specific commands for my CPU here. I mean, okay, jump is pretty common, but sub, sure. What is Rio? What is whack? Like, that's not really self-explanatory. Those are details about my CPU that are not really clear. And it's a bit of a pain to keep track of. Okay, I need to keep in mind what's currently in the accumulator. I have to write the stuff to the accumulator and then evaluate it. I have to write it there and then copy it over to somewhere else. You always have to keep track of how is your CPU currently structured, which value is stored where, how is everything arranged. Wouldn't it be great if we didn't have to think about all of that and just focus on, this is the basic algorithm, this is what we want the computer to do, and the computer just figures out how to do that itself? Whatever. So let's make our life a bit easier. So start with something simple. In our program, basically in the last examples, we always had in the end this block of just, here are a couple of values we want to use for our program. It's always a block of just numbers. We gave some names we could use in our program. We had to just put them somewhere. We just put them in the end so they don't interfere with our actual program by accidentally being processed as operations. What if we made our life a bit easier? Instead of doing that all by hand, we just give it the instruction, hey, I want an A, I want a B, I want a product. And the computer will just do that for us. Wouldn't that be great? So you can see, going from here to here, not really difficult for the computer. As long as we somehow define a define. If we tell the computer, hey, look out for this word, it has a special meaning. If you see this word and there's some text behind it, please interpret this text in a specific way and create some additional lines of code that follow a specific pattern. In this case, just look for define, look for the terms that come after, that are separated by, in my case, commas or space, and just write them out as individual lines for variables. And since we're gonna be fancy anyway, let's add the jump instructions to make sure that if our program at any point ever reaches this block of variables, instead of risking that it interprets it as operations, just make a jump that directly goes after the block. So if we ever reach this point, it will just move down here and never try to read the values directly. Just a protected area. We don't have to type this out ourselves, so this is pretty convenient. And if we add it, why not just tell it, hey, also start with a value other than 0. Like, can also do that, no problem. Like, it's all the same for the computer. And that means we can also do a lot of other stuff. Let's see, 9 equals 9, and some value, and another. Just write them out. We don't have to think about them anymore. We just set out our program as, okay, I know I'm gonna need these values. Computer, do the rest for me. Done. Then going further, let's have a quick look at our program again. Where is it? Here. what's one of the first things we did here? We read the value of a b and checked if it's 0, because multiplying by 0 is 0. We can just skip everything and jump directly to the end. Well, if we have this pattern repeatedly, also sort of here, why not put that into words as well for the computer to write for us? Instead of writing 2 lines that tell us, hey, please read the value and check the value and do something based on the value, let's just write some code for us, dear computer, that does exactly that. And we can do that in this case. Let's say we have an A10. So again, this is just creating this block. And then skip if A is 0. Skip. Then A. Whatever. Maybe CA like that. Oh, actually, let's be weird like that. So if we look at this now, this is our block we had before, like just this define in the top. We can ignore this right now. This right IO, this is what we had in here, between these 2 lines that contain the word skip. And then down here we have the read IO, the last one I wrote down in the end here. So if we look at the changes, this line and this line, what do they do? Well, we read the value of A, then we have this jump instruction with some weird values, same as here, same weird values, and then there's a NOP operation down here, and that's it. Well, what we're doing here, let's separate that out. This block and this block is where we added the additional lines, these skip lines. We just tell the computer, hey, I want to have a certain amount of code execute or not execute based on the value of A. And so the computer knows, well, to do that, I just have to write A to the accumulator, then use an instruction to check if it's 0 or not. And then either I'm executing code because the condition was false, it's not 0, or I'm gonna jump to the next part of your program down here. Thing is, our computer is not too smart, so it knows it has to skip this part here. It doesn't know it has to start here. It just knows it has to skip up to this point. So when we replace everything, it just invents a new command itself that we didn't write. I never intended to have a NOP in here, no operation. Just invented it itself, inserted it, and decided this is where we're gonna jump. Because it knows this NOP is harmless. It's wasting some time, sure, but it's not doing anything else. It's not changing any important data. And once this NOP executes, it will automatically go to the next instructions, the actual instruction that we wanted. So going from this to this made it a bit easier to write the code. It's a bit more easy to read and to understand. It also has the downside that, right, we have some wasted space in the memory and some wasted instructions later in the code execution. There's a trade-off. The computer isn't too smart about it, but it is pretty simple to do still for it, because we just replace more text with other text. The same thing we did before for things like replace the 3-letter combination for different operations with a number, just a bit more fancy. But it's still just, if you see this text, well then take whatever this is and make sure you load it into the AC and check it. And if you think about earlier, we had the weird combination where we had to suddenly invert a condition. Well, the computer can do that for us as well. If I expand this now, we get some more text and some more ridiculous symbols. Well, since the computer has to write code that can be run, it has to include these references, these names everywhere, just like we would if we write the program. But it might interfere with actual symbols we use. Let's say it would just use the term jump or end or whatever. Well, we might use the same name somewhere else, and that's going to be a problem. And just telling us, hey, you are not allowed to use this specific name anymore, that's annoying. So rather than using some common terms, I'm using certain symbols that technically I might be able to use, but very unlikely. If I just keep it to myself as a rule, hey, don't write any weird symbols, keep it at simple letters, then I'm never gonna have any conflict with whatever the computer comes up. And let's have a look at the code. So we want to skip this entire thing unless the value in A is a 0. So if A is 0, we want this to execute and then go to RIO. So we want WIO and then RIO. If A is 0, we want to just RIO. Let me look at this. This is the block for the definition. Here's our WIO, RIO. So down here we still have this knob, because the computer still has to find a way to mark the position we jump to without knowing what's coming after that. So maybe there is code after that, maybe there isn't, we don't know. Now I wrecked the entire program, didn't I? Whatever. And up here we have the same construct we had earlier, where we combine our conditional jump with a normal jump to invert it. So if we look at this text, it's coming up here. And it's the same construct with a knob that we put in as a placeholder, so we don't have to worry about whatever actual instruction comes here. Again, additional overhead. Like, this will make our program technically bigger and slower, but it makes it easy for the computer to just replace our text from earlier with actual instructions. That's the trade-off here. Well, from this to this. Now let's say I don't want to just skip certain content, I want to repeat it. That's what we did all the time in our algorithms. We had to repeatedly add, we had to repeatedly shift over and stuff. Well, you can just repeat. As long as until A is 0. So we just write more some text. It's pretty understandable. Repeat until A is 0. So we want to repeat this WIO continuously until we reach a point where A is 0. Of course, at this point, this program doesn't really work all that well anymore. Let's do it this way around. This is where we actually have a way to stop the loop at some point. So if we compile this down, we have this define block again. We have our RIO and WIO. This time, however, we have a bit more code. We don't just have a knob down here, this time we have a jump as well. But on top here, we still automatically have the value of A written to the accumulator. Then we have a conditional jump if it is 0. And we jump down here if it is 0 to end the entire loop process and just go to the output. Or it is not 0. In which case we call RIO and then call it unconditional jump, just go straight up back to the top to here where we read or write the value of A back to the accumulator and check it again. So execute this part repeatedly until at some point A will be 0, and then we go down here and continue with the program. Actually, maybe let's just try that, because I'm curious. I've never made a repeated input. So this is our first input, because right value, let's do 1, and we have a loop. Let's use 1 again. So unless I put something else in, this is going to repeat forever. So let's actually put a 0 in here. And we output the 0. I mean, the program doesn't really make much sense, but it works. So let's go backwards here. Repeat until. We can also do it the other way around. We can do the inversion. Repeat. No, not unless, while. Sorry, that was a skip. Different terminology for different use cases. Repeat while a is 0. So if we look at this, for definition, we have the RIO, we have the WIO. Now we have this block down here again. We jump back up to the top to repeat our code, or we have the knob just as a placeholder to we're done. But up here we have now this inversion. We jump to this knob if we want to continue internally with the block, or we just skip, the condition is not true, and use this jump to go to the end. So it's still very simple code. Like, it doesn't take much. You just have to look out for the text, and there are some certain conditions you have to look out for. There's maybe an even easier one. Instead of checking for the value of a, maybe you just want to check if the flag is set. Well, in that case, we don't have to write the value of a to the accumulator. We just directly jump if the flag is set. It's the exact same condition. We can do that also for the skip, like skip if flag. Even doesn't make much sense now. The program, there's no write to the accumulator anymore needed. We just run the check and continue or not continue based on that. So some texts can be used to make our life easier. And let's use one more. Another piece of code we had used a few times is just moving bits around to store data and read data and manipulate data that's in the memory by continuously loading it to the accumulator, doing operations, storing it back. And last time we made the mistake of forgetting to storing it back, which was actually a bug that cost us some time. Well, what if we didn't have to keep track of all of that? That's A to... It's B. Second one to B. So our definition is a bit bigger now, because we have an A and a B. And our one line is just translated into write B to the accumulator and read the value back into A. Set A to B, or set B to A works as well, of course. Write the value of A and read it into B. Just straight up copy from one place to another. We can do some more stuff, because computers are pretty fancy, pretty smart, and absolutely good at recognizing certain patterns. If I just decide, hey, if you see this after our little text, well, we're just going to add some more operations. Read the value of B, you add the value of A to the accumulator, and then you write the value back to A. So instead of keeping track of what's in the accumulator, what's not in the accumulator, how do I have to roll from where, just tell the computer what I want. I want to set the value in A to whatever is currently in B plus whatever is currently also in A. No thinking about the accumulator at all. I can also do minus, of course, for the sub. And something we used earlier, shifting over to the left or right, which I'll just do with a little arrow to the left or to the right. Shift it over by one bit shift. Maybe I want to shift it over twice for some reason. Well, then just use 2. That works just fine. And since we already have a system that can just add new variables, why not make it simple? Instead of especially defining something like, oh, there's a 0 and a 1, well, just write the constant in here the computer already knows that this line is special somehow, so we can attach some more specialty to it. And if we expand it, well, we see down here it adds another block where we defined the constant we used. So there is a lot of fancy stuff you can do by just having the computer take some text you write and replace that with a certain pattern of code. It's not that the computer can freely create any kind of code based on input. Don't confuse this with AI code. Please don't confuse it with AI. Not that crap. This is just straight up looking for a specific predefined pattern and generating a very specific pattern of code based on that. In this case, actually, I just use regex. But there are simpler ways to do that. Well, let's use these abbreviations, these shortcuts, to write the same program we just did again, this time hopefully shorter. So let's look at the notes again. If they show up, let's make all those disappear. So that's all code from earlier. Let's try to write this again. So first, we need a couple of variables. So we're gonna need A, we're gonna need B, and we're gonna need product. So done. So then we want to check if A is 0, and if it is, we jump to the end. So that means if A is 0, we go straight down to the end. So this entire part is skipped. And we just have the command for that. Skip if A is 0. We just tell it down here is where we want to stop skipping. And after this comes the code that we want. And that's output the value of the product. And that's just input output, just write the product. Okay, so we've done this part. We defined A and B, we still have to read them. So let's do that up here. We read A and we read B. That's done as well. We got that earlier. If it's not 0, then we go into the whole block. We start to actually multiply and then shift A right. All right. So we set A. Let's indent that here. Set A to A, shifted to the right by 1. Alright, done. Then we check if the value was set, if the flag is set. If yes, we want to execute this code. If not, we skip this code and go directly down. So we can either skip if set. No, we want to skip unless set. That's flag. So if the flag is set, we want to actually do this code, and this code is add B to product. So set product, and write product to B. Well, actually, we want to add B to the product, so set product to product plus B. That takes care of this one. And then we have to just shift B to the left by 1. Alright. Set B to B, shift it over to the left one. And that takes care of this one. And now we just have to add the loop that goes back up. So this could contain the check if A is 0. So that means we have to repeat, and we repeat unless, no, we repeat until A is 0. So actually this is not a skip anymore, this is repeat until a is 0. But we do want to have the skip if b is 0. Want to still have that skip that I didn't write in the code here, and skip. Like that. Code is getting a bit large. Alright, but basically this should be it. I did everything right. So, this code, first we're gonna get rid of the white space, of course, and then we're gonna replace all our little fancy instructions here with code. Looks hideous, but should still work. The good thing is we don't have to understand it, the computer knows how this works. Let me just put it in line, clear up the references, replace the opcodes, and then we can load it in the computer. And let's just go back to the computer and just test it. Okay, wants an input, 6. Let's make it simple. We just run through our program. Well, that is the end result, 18. It works. So our program worked. And it's all just step down from here, which doesn't look too friendly. But I bet even if you don't know programming, it should be pretty easy to understand what's going on. Like if you look at it for a while, except for these commands, the entire rest, like this thing and this part, should be pretty self-explanatory. That's how it's designed. It gives a clear, readable instruction of what's happening, like a more abstract idea of what is this supposed to do. And it's still written in a way that a computer can figure out the pattern and replace it with another preset pattern that's just more complex. But yeah, this is basically our way to the higher level languages. This is how we went from just assembly to actually programming languages. That's when we had more and more people start to develop code and more advanced computers that would require more advanced code. And essentially, at least the language we're going to look at, C#, is basically this, but with some extra steps. The patterns get a bit more complicated, but in many parts, the language that we're going to look at is following this trend, actually. Pretty straightforward. It doesn't sound the same. The text is a bit different and the exact formatting, but the basic idea is still the same. We tell just, for example, this piece of code, please do not use this code or run this code if this condition is not true or is true, rather. Or this piece of code, please repeat this until another condition arises. And in between, please change the memory address to another memory address and make certain operations on that. And don't let me think about what's actually going on in the computer. Which is another advantage of languages, higher level languages. Because if we ignore that I have these specific commands still in here, this part is not really tied to my CPU. I could have a completely different CPU that probably would be able to still recreate the logic of this code in a just very different way. So if I just write the logic out, I can have the computer then create machine code for different CPUs, for different machines. Instead of having someone design code that will only work on one specific machine, you can now have someone write code that just describes the general logic and have then different computer programs just turn that logic into actual executable code for the specific machine. That's why we have compilers or settings for compilers, which can turn your source code later on into code that runs on very different machines. Though usually we don't focus on the hardware and more on the software, more specifically the operating system. That's why you usually have the difference. Though 32-bit and 64-bit is still a topic, though that still counts as machine-based, I guess. Anyway, this is today's lecture. Just a demonstration of more advanced concepts. Maybe a bit too advanced, that took some time out. We're skipping over a big topic today. I guess we're gonna have to pick that up once we hit that roadblock in the actual C# lessons, which we're gonna start with next time. For the most part, this is it from the basic simple CPU setup. I'm kind of regretting letting go of this. Took way too much time to come up with it. Oh well. Yeah, thank you for joining in. And I'll see you next time with actual C#. Goodbye.